What's up, everybody? Now we are going to talk about something called Hermite Fujiwara matrix. Okay, and unlike the previous video where we were talking about something called Bezout matrix, right? We had like two polynomials, f of x and g of x, two polynomials, and by doing some type of process, right, we computed a matrix. Okay, all right. Matrix, each entry, whose entries are being populated by constant numbers, just numbers, right? No, symbolic variables like x and y or something, just numbers. All right. And here in Hermite Fujiwara matrix, in this topic, right, this is again some type of formula. You don't need to know what it is exactly, or why that formula is something that we use, right? You don't need to know that, right? And okay, some type of process, right? And then we are going to have a matrix. Okay, first of all, you have one polynomial, right? Okay, and then some process, and then that process will yield us, right, matrix. Okay, whose entries are just constant numbers, given the coefficient of this polynomial is constant, right? Okay, if this is like 3x squared plus 1, the matrix the entries will be made out of constant numbers. Okay, however, if this is not like that, and if this is like a1, right, or a2 x squared plus a1 x plus a0, if this is something like that, then the matrix will have like a1, a2, a0, those type of terms. Okay, all right. So wanted to make that clear. Okay, all right. First of all, the first subject is star operation, f star here. Okay, here we have f of x. Okay, and then this star operation here, something that we need to learn now, just f of star is f of minus x. This is it. Okay, and of course it is something that MATLAB can do easily, right? All right. Okay, and I am looking at my screen and I am looking at my notes. Okay, there is nothing I missed. All right, so how do we generate Hermite Fujiwara matrix? Okay, first maybe 0, you have f of x. Okay, first step, compute f star of x. Okay, 2, compute Bezout matrix of f and f star. Okay, and then 3, construct Hermite Fujiwara matrix. Okay, all right, you have f of x. Okay, and then you have f star of x, which is literally this formula, right? Okay, and then compute Bezout matrix of f and f star. Okay, and it is this formula, by the way. Okay, by using this formula, and we have talked about the Bezout matrix in the previous video, right? So you can check that out, right? Just a simple procedure, right? But we are not going to talk about the details of constructing the Bezout matrix. Okay, all right, and then construct Hermite Fujiwara matrix. How? When you have the Bezout matrix of f and f star of x, okay, you are going to, and this is your row number 1, this is your row number 2, and this is your row number 3, and this is your row number 4. Okay, and you are going to wait a sec, let me change the thickness. Okay, I guess highlight your rows with double indices. Okay, for example, this is row number 2, and 2 is a double number. Okay, even number. Okay, and here this is row number 4. Okay, and all right, you just highlighted that and multiply the entries that are located on those highlighted rows, right? So you have here 1 2 3 4 5 6 7 8. You have 8 entries, and multiply each of them, right, each one of them with -1. Okay, all right, each one of them with -1. Okay, and then what you get is Hermite Fujiwara matrix. Okay, you don't need to know about the details why this is something that we use, right? We are going to use, by the way, so far what we have learned is, sounds a little not useful, right? But in the next video, we are going to talk about a very important subject, and static output feedback control for RTI systems. All right, and okay, and we are going to use this object, this mathematical object called Hermite Fujiwara matrix, in that subject, right? Just constructing a control law, just static output feedback, right? Static output feedback, and for ATI systems. All right, okay, and I am looking at my notes right now. So okay, and now let's talk about an example, right? And this will be like a hard example. All right, so let me check my notes. Okay, first of all, you need to have a polynomial. All right, let's write down our polynomials, f of s, and as soon as I name my indeterminate s, right, you should kind of think, hey, maybe this is something about characteristic equation, characteristic polynomial, or with transfer function or something, right? Numerator or denominator of transfer function. Maybe this is something that we are going to talk about in the future, right? You need to think something like that. And okay, f of s equals a sub 0, okay, plus a sub 1 times s plus a sub 2, okay, times s squared plus a sub 3, okay, and times s cube. Okay, all right, this is f of x, I'm sorry, f of s, okay, and all right, and these are our coefficients of this polynomial. All right, and then for the sake of using this formula, for the sake of facilitating what we are going to do now, right, just construct f of x, right? Because we were talking about f of x, right? And so structure our problem such that we will be able to use our general purpose program or function, right? MATLAB commands. All right, f of x, f of x. Okay, here just change the s with x. Okay, all right, should I write that? I think let's write it. Made my mistake, right? Again, a2 x squared plus a3 x cubed. Okay, great. And then construct f of y. Wait a sec. Yeah, f of y, because why because we are going to use this formula, right? And then we are going to, construct our Bezoar matrix and then Hermite Fujiwara matrix. But now we need to structure our what we have so that we are able to, use this formula straightforward, right? Okay. And we have f of x, right? And we need f of y, and we need f star of x. Okay, that's great. A0, A1, A2, A3. Okay, f star of x. What was the, formula here? This is it. A star minus A1x plus A2x squared minus A3 x cubed. Okay, and then f star of y, just substitute y for x. Okay, okay, so we have f of x, f of y, f star of x, f star of y, right? Those four polynomials, and let's use that polynomial. Of course, we are not going to do that, inconvenient computation, and we will use MATLAB for that, right? And then we are going to construct our Bezoar matrix, okay? And then we will do this basic row operation, right? And then we will have our Hermite Fujiwara matrix. So, okay, let me change this screen. Let's go to MATLAB. Okay, first of all, we need to define our symbolic variables a0, a1, a2, a3. Okay, and this is our f of s, right? Here, s is our indeterminate. Okay, right? Okay, and then we need to construct f of x, right, by using subs command, and then f of y by using again subs command, right? This is makes sense. And then f of minus x, right? Or this is something that we called f star of x, right? Okay, f of minus x or f star of x. Okay, f star of x equals f of minus x. Okay, right, and the same for this f of f star of y equals f of minus y. Okay, this is like a total tongue twister, but let's move on, right? And then this is our formula, right? Okay, let's keep keep this in mind. Okay, let's get back to our tablets here. Just look at this, right? This is something that we are using right now. F of x times f star of y. Okay, let's change the screen. F of x times f star of y. Okay, right, great. And right, and the expression. Okay, let's compute that. Okay, this is like a very large expression, right? Okay, and now again, just let's ask ourselves what this is. This is an expression. This is a polynomial expression, bivariate expression, right? The determinants are indeterminate are variables are x and y, right? Those a0, a1, a2, a3, right? Those are our constants, right? Okay, constants. But these are indeterminate variables. X and Y are indeterminate variables, but those are A0, A1, A2, A3, right? Okay, those are constants, right? Okay, and so we are going to now construct our Bezier matrix, and those A0 and A1 are coefficients, right? A terms are coefficients will be, will appear in that Bezier matrix, basically. Okay, great. So we will now, okay, just use this to get our n number, right? 3. Okay. Why? Because our degree of our polynomial is 3. Okay. Here s cube, right? Okay. And then let's construct our Bezier matrix. Okay. Let's initiate it by zeros. All right. And then like we did in the previous Bezier matrix video, tutorial video, right? Just compute the Bezier matrix for this x and y in polynomial, right? Okay. So let's just, by the way, again, just one sec. Get coefficient is a function, is a custom function, right? And whenever you have some expression, and a polynomial expression with x and y, okay? And by the way, unlike the previous video, right? This time our coefficients, they are not just constant numbers like 2 or 3. They are not like constant numbers, but they are symbolical variables. Okay, a1, a0, a1, a2, a3, etc. Okay, all right. Whenever you have some polynomial, by the way, coefficients can also be symbolic variables. Great. Whenever you have a polynomial x and y, okay, bivariate polynomials, and whenever you want to get the coefficient of some term, for example x times y, right? You give me this polynomial and you ask me, hey, what is the coefficient of x times y? What would I tell you? I will tell you 2 times a0 times a3, right? This is what I should give you, right? Okay. And this get coefficient custom function, meta function, is able to get the coefficient of some term that you entered, right? Okay, all right. So maybe expression 1. Okay, I should rename that because it kind of makes sense, right? And xy, and I should term 1, right? Xy term. Okay, maybe maybe I should make it something like this. Xy. Okay, you have an expression, right? Polynomial, bivariate polynomials. Okay, polynomial, indeterminants are x and y, all right? And then you give me, you also query some term, right? X and y term, for example, x squared and y squared, right? You give me some term, and I will give you, or this function will give you the coefficient of that term that you queried, right? Okay, 2 times a2 times a3, for example, if you entered, right, x squared times y squared. Okay, great. All right, because in the previous video we only talk about the x and y polynomials where the coefficients were like in just numbers, right? Okay, and this is like, now we are talking a little bit more complicated thing where our coefficients are again symbolic variables. Okay, that's great, and so let's run it and construct Bezier matrix. Okay, this is our Bezier matrix. Okay, again, let me write down some comments. Okay, here you have f of x and f star of x. Okay, Wait a sec. And this is the Bezoar matrix. Okay, this is the Bezoar matrix. Okay, and then what you need to do is to multiply with -1, right? Negate the entries that are located at the rows whose indices are even numbers. Okay, even numbers, right? Okay. For example, this is for loop, and we start from 1 to we are going to iterate over our row indices. All right, and let's check it. If the index of the current row is even, if even, right, then multiply with -1 all the entries. This is rows and columns, right? This is for the current row and all the rows, right? Or this means that all the entries in that row. Okay, all right. You multiply it -1. Okay, all right. So here you can look at this. Okay, they will be negated, and I'm hoping we didn't make a mistake, right? Wait a sec. Let's start from scratch. Okay, all right. Okay, and then let's run it. Wait a sec. I feel like it's not working. Wait a sec. Alright, now continuing. I just got confused, right? It was working properly, alright? And I thought it wasn't. Alright, so again, let's construct our Bezoar matrix. Okay, this is our Bezoar matrix, right? Now what we are going to do is we are going to negate, right? Multiply it with by -1, right? With all the entries that are located on this row, second row, okay? And then this, for example, this will be 0, this will be 0, and this will be minus of this expression, and again 0. And this is third row, not index 3, right? And this is again a even row, okay? And we are going to multiply it with 0, right? Okay. So what we will see should be, right? This should be 2 times a1 times a2 minus 2 times a0 a3. Okay, this is what we have, right? Okay, so and it would be better for me to name this as Hermite Fujiwara matrix. Okay, just let me do that. Okay, right, this is what we have, right? Okay, so let's change the, wait a sec. Okay, and I want to make some confession that I was kind of making a mistake, right? It's not a big mistake, but let's correct that. We don't need to construct n+1 by n+1 matrix. Okay, just n by 1, n by n matrix is we need to construct. Just I change this line, okay? Because those last column is made out of zeros, right? And then this last row is made out of zeros, right? And okay, so let's again, for the sake of completeness, let's run it. Okay, we have f of s, okay, and then we constructed our f of x, f of y, f of minus x, f of minus y, right? And then we use that formula, right? And okay, and we have bivariate polynomial, okay, and then we just change this part. We get the degree of our f of s polynomial, and that is 3, okay, and then construct is, you can consider that as some type of memory allocation, 3 by 3 zero matrix, but we initiated as a symbolic variable, right? Okay, and let's iterate over the entries, okay, and for each entry, okay, there is a corresponding term, okay, and then get the coefficient of that term from this polynomial, okay, and then write it in the corresponding position of a matrix, right? So let's run it. All right, now we have this, okay, and then negate all the entries that are located in a row whose index number is even number, okay, right? This is row number 1, row number 2, right? Okay, so if this is even, right, so negate it basically, okay, and we have only one row to think about, right? And to do that we use this code, right? Just let us do that. Okay, here this is Bezoar matrix, and this is Hermite Fujiwara matrix now, okay, because we negated that. This is only, yes, the relationship between Hermite Fujiwara matrix and Bezoar matrix. Okay, right, great. Again, we negated that. Not only this entry, but all the entries that are located in a row whose index number is an even number. Okay, great. All right, and again, MATLAB code does that, right? So you don't need to think about the details, but at least be aware of the process itself. Okay, again, we have talked about the get coefficient function, right? Okay, so let me get back to the tablet, right? Here, first of all, this is characteristic polynomial of a CISO or MISO or SIMO, I mean, system, right? But let's, for the sake of example, right, consider a CISO example. Okay, this is a characteristic polynomial of a CISO system. Okay, all right, characteristic polynomial. All right, you have this, okay, and then you are going to construct your Hermite Fujiwara matrix through the process we just talked about here. Okay, all right, and for this CISO system to be stable, this Hermite, right? You have CISO system and you have some characteristic polynomial, all right? And by using that characteristic polynomial, you are going to construct a corresponding Hermite Fujiwara matrix, okay, and this is stable if and only if this Hermite Fujiwara matrix is positive definite, okay, all right, and this is positive definite, right, if and only if let's call it our CISO system. The CISO system is stable. Okay. All right. So what is the, I guess, use of computing, constructing our Hermite Fujiwara matrix is this. You have r plus minus, some type of controller, right? And maybe you have k1, k2, k3, okay, some type of controller with parameters k1, k2, k3, okay, and then you have some type of e of s, okay, then this is y, and then what you have is a closed-loop system, okay, and okay, right, and you get the characteristic polynomial, okay, and probably the, okay, let's run an example. All right, let me check my notes. Okay, let's run a specific example. All right, okay, here. All right, I think we should do example in the next video. All right, we are running out of time. Okay, and okay, but let me conclude my statement. You have this type of control system, closed-loop control system. All right, and then you will have this closed-loop CISO system. All right, and then you will get the characteristic polynomial, and then you will get Hermite Fujiwara matrix. All right, what do you think the structure of that Hermite Fujiwara matrix will be? Right, I think, right, it will be like, of course, it will be a symmetric matrix. I mean, by definition, it must be a symmetric matrix. Okay, and each entry will have k1, k1, k2, ki maybe, right? Each entry will be a function of ki. Okay, all right, and then this Hermite Fujiwara matrix, corresponding to this closed-loop system, must be positive definite, right? Okay, and by using that constraint, you can determine what should your k1, k2, k3, controller parameters should be, right? Okay, and you are aware of course, root Hurwitz, criterion, right? Stability criterion, right? And this Hermite Fujiwara matrix is, and this root Hurwitz criterion, they are closely related, but in my opinion, Hermite Fujiwara matrix process, let's call it, right, and is something, I think, something that can be described as more algorithmic, in my opinion. Okay, all right, and let me tell you this as well. And finally, in the next video, we are going to look at an example, right? And we are going to, look at this type of closed-loop for CISO plant. We are going to construct a control law, and then we are going to draw our closed-loop control system, and then we are going to determine the constraint, right? The constraint, for example, this is a constraint, right? Okay, we are going to then construct our Hermite Fujiwara matrix corresponding to the closed-loop system, and then for this closed-loop system to be stable, the corresponding Hermite Fujiwara matrix must be positive definite. Okay. And by using this constraint, we are going to impose some constraints on our controller parameters, right? K1, K2, K3, right? For example, it can be a PID or something, right? Okay. And you are going to see that, for example, if each entry is like a linear function of ki's, right? What would you say about that, I guess, constraint? You would say, yeah, this is an LMI constraint that we can handle with, right? However, it will not be an LMI, but not all hope is lost, right? It will be a BMI, right? And which is not body mass index, which is bilinear matrix inequality, right? And again, there is some hope that by using like pen BMI, right, or BNB BMI type of like optimization solvers, right, and using MATLAB and YORMIP and those type of BMI solvers, we can again determine and or compute those ki, our control parameters, right? And in the next video we are going to look at an example where we construct a static output feedback control flow. Okay, we are going to construct that type of static output feedback control, right? Okay, and let me tell you, you can only solve this problem for a very limited, I guess, dimensional problems, right? And again, like CISO system is like really, you know, I guess constraint limited type of problems, okay, that you can handle. But it is important, right? It is an important subject, and I don't think there is much enough material on YouTube and also on the internet, right? All right. Okay, that's it for today, and thanks for watching.